Let's talk about the net force. We've been talking about net force. Today we're going to be looking at what I like to call statics. And there's the example of the bridge that we put together here in class. And so those of you guys that are away, I guess I'll have to show you the bridge again. And you saw me stand on it using my Chris Angel powers, right? As I levitated above the bridge. So you guys at home missed that. Yeah, it's pretty cool. So, in the absence of force, objects at rest stay at rest, and objects in motion continue in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. The forces cancel each other out, and there is no net force. It's the net force that changes an object's state of motion. That's kind of important right there, right? It's the net force that changes an object's state of motion. Figure 410 shows how forces combine to produce a net force. When you pull horizontally with a force of 10 newtons on an object resting on a frictionless surface, the net force action on the object is 10 newtons. Duh. If a friend assists you and pulls at the same direction with a force of 5 newtons, then the net force is the sum of these forces, or 15 newtons. The object moves as if it were pulled with a single 15 newton force. However, if your friend pulls with a force of 5 newtons in the opposite direction, then the net force is the difference of these forces, or 5 newtons. The resulting motion of the object is the same as if it were pulled with a single 5 newton force. That's all basic review there. There's nothing too new in your mind. Okay, this is where it gets important. Equilibrium, when the net force equals 0. Right? Whoa, what happened? When the net force equals 0. What force is acting in your book while it's motionless on a table? Don't say just its weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. The other force is the support force of the table. Support force is often called the normal force, and again, that's a review from grade 11. As shown in figure 411, the table pushes up on the book with a force equal to the book's weight. When an object is at rest, with the net force on it being 0, we say the object is in a state of equilibrium. Equilibrium. The resting book is in equilibrium. Does the table really push up the book? Yes. Just as the spring pushes up on your hand when you compress it, look at figure 11 right here, right? You can feel the spring pushing back in your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between the book and the table would feel it's being self-squashed from both sides, right? You wouldn't feel it just from one side. When you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope. A rope under tension will twang if you pluck it, like a guitar string. How much tension is in the rope when you hang from it? If you are in equilibrium, the tension must equal your weight. The rope pulls you up, and the force of gravity pulls you down. Since the equal and opposite forces cancel each other out, you, of course, hang motionless, which is what you want to do. Suppose you hang from a bar suspended by 2 ropes, as shown in figure 412. Neglecting the weight of the bar, the tension in each rope is 1/2 your weight. The total tension force acting upward, half your weight plus half your weight, balances your weight, which acts down. When doing pull-ups using both arms, each arm supports half of your weight. Have you ever tried pull-ups with one arm? Why is it twice as difficult?
Not difficult.
Well, for some of you it might not be, right? Right? But you have to pull all of your weight with one arm instead of spreading it over 2. A spring scale can be used to measure tension. When we weigh a bag of apples by suspending it on a spring, the scale reading tells us the weight, considering a 1 kilogram bag of 10 apples weighing about 10 newtons. When suspended by a single vertical scale, as shown on the left in figure 413, the scale reads 10 newtons. If instead we hang the 10 newton bag from a pair of vertical scales as shown on the right, no problem. Figure 413, each scale will only read 5 newtons, and I'll grab some scales and I'll show you that in a minute. The 2 scales pull up on a combined force equaling the bag's weight of 10 newtons. Since the bag hangs at rest, the net force on it must be 0. The key concept is this: if a 10 newton bag is in equilibrium, the resultant of the forces applied by the pair of springs must equal 10 newtons. If the spring scales are oriented vertically, this is easy, 5 newtons each, right? So 1 scale, we got 10 newtons, 10 newtons. 2 scales, if we've got 10 newtons of weight, we've got 5 and 5. But that's only if they're vertical. What happens if you put them sideways? Okay? Well, what will happen to the tension? It will become higher. Let's consider now non-vertically oriented spring scales. The tension is greater in a pair of non-vertical spring scales and depends on their angle from the vertical. This more complicated situation is most easily understood using vectors. Recall our treatment of velocity vectors from Chapter 3. We'll now use the same vector addition techniques with forces. Force, like velocity, has magnitude and direction and is a vector quantity. Look at the left of figure 4.14. Notice that when the spring scales hang at 60 degrees from the vertical, their readings are 10 newtons each, double the tension of the vertical hanging scales. Why? Because the sum of the two tension vectors must support the downward acting 10 newton weight. The sum of the vectors must be 10 newtons directed vertically upward as shown by the diagonal of the parallelogram formed from the two vectors. For an angle of 60 degrees from the vertical or 120 degrees between the scales, 10 newtons of tension force is required in each scale. For angles greater than 60 degrees, the scale reading would be increased even more. And here's the math behind it. Let me show you. Okay, so if I've got 10 newtons down, right, how come I need 10 and 10 then? Well, it's because the vertical component there and vertical component there, each one of those would be 5 newtons. And if this is 5 newtons, then this hypotenuse here has to be greater, doesn't it? And the greater that angle becomes, the longer that hypotenuse must become. For me to get 5 newtons there at that angle, I need a huge hypotenuse. I need 20 newtons. As the angle becomes wider and wider and wider, way, way more tension. Does that make sense? And you can actually do the calculations to figure it out. Notice that on the right of figure 4.14, the angle from the vertical is increased to 75.5 degrees. At this angle, each spring must pull with 20 newtons to produce the required 10 newton vertically upward result. As the angle between the scales increases, the tension in the scales must increase for the resultant to remain 10 newtons. In terms of the parallelogram, as the scales angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain the same at 10 newtons. Let me show you here. So if I need 10 newtons right there, and I need 5 right there, right? 5. Why do I need only 5? Because I've got two scales, right? So I need 5 right there. And this angle here is 75.5. This is my hypotenuse. This is a right triangle. This is adjacent over here, this side, right? So cosine of 75.5 is my adjacent, 5 over my hypotenuse. So my hypotenuse is 5 divided by cosine 75.5. Somebody do the math, please. What's 5 divided by cosine of 75.5? Somebody, do the math. Because I want it to be proved.
Why did you do it? Cos 75.5?
Because this is because that's what that angle is right there.
19.96. It says it's 5 newtons.
19.96, right? Which is 20 newtons.
I'm still in radians. Right?
Yeah, get out of radians.
I was in pre-cal, okay? Wait, sound goes.
Could you also do it like 5 cos 75.5 equals?
No, because cosine is adjacent over hypotenuse. And when you isolate for h here, the h goes there and the cos goes down below. It has to be 5 divided by, right? So it's 19.96. If you understand this, you understand why a vertical clothesline can support your weight, but a horizontal clothesline cannot. It'll break almost immediately. How come? Exactly. Like here, if this person weighs, we'll say 500 newtons, and this person weighs 500 newtons, all that has to happen here is 500 newtons in that string, right? But this one that's like this, you're going to need like way more than 500 newtons, right? Because it's going to drop like this. This little bit has to be 500, which makes the hypotenuse much greater, maybe like 30,000 newtons, depending on the angle. For any pair of scales, ropes, or wires supporting a load, the greater their angle from the vertical, the larger the tension force in them. The resultant of the tension forces, or the diagonal of the parallelogram they described, must be equal and opposite load being supported. As you'll see when you answer the following question, the parallelogram technique of adding vector yields some very interesting results. And before I do that, I just want to show you with the actual scales. So, with your clickers, go and get a clicker. Okay, so here's question 1. There's 4 questions here. When you step on a bathroom scale, the downward force applied by your feet and the upward force supplied by the floor compress the calibrated spring. The compression of the spring gives you your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on 2 scales with your weight divided equally between them? So you've got 2 scales, like so, right? And then here you are standing like so. What will each scale read? Will it read your original weight divided by 2, your original weight times 2, or I don't know. I'm waiting for 2 more people.
Oh, right, let's do it.
Hey, Riley's already done it.
It is. It's a trick question. It's not a trick question, I know what I'm doing.
What happens if you stand with more of your weight on one foot than the other?
Wait, you start this.
Like, what if you sort of lean one way? What? What happened with that?
It's still there.
No, you're still there. You're good. What if you kind of lean one way? The scale you're putting more weight on will show more. The scale you're putting more weight on will show less. They will still show equal weight, so they will still show your original. Really not trick questions.
What is it? What do you mean?
If you lean on more on one way.
Hey, hurry up. These questions out.
How do you guys know it's me?
Because it says up on the screen who we're waiting on. If the children on the swings are of equal weight, which swing is more likely to break, A or B?
I'm gonna be first.
Each kid weighs the same.
I go, you were, okay.
You are team number 5 to arrive. Okay. Consider what would happen if you suspend a 10-Newton object midway along a very tight, horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? Will
Where's
this?
that one?
Oh, I didn't give you the answer. I just gave you the question before. Will there be a sag?
Wait. Oh, what?
Wait.
Is it possible for the string to remain horizontal without a slight sag?
What? The button?
Is it there's a Y and an N button.
Oh, there's. Oh. There you go.
Mike, we're waiting on you. There we
I
go.
clicked the button.
Excellent. Yay, everyone got it right. No, it's not possible, right? Adrian and I showed that. We actually broke the string, right? Not possible. There's always going to be a dip. There has to be. Why does there have to be? Well, because there is a downward force, right? A weight force, so there has to be a vertical component, and the only way for there to be a vertical component is if there is actually an angle. There must be an angle. The answer to this one is, of course, B, at the angle. What happens if you stand on more? Obviously, the scale you're putting more weight on will show more. That's A. I think everyone got them all right. Yay, everyone got 100%. Your averages are going up.
Double tap.
Mr. Bennett, you are an amazing teacher. Okay, there's the picture of the bridge.
You make extremely easy quiz.
Thank you. Now, the Romans knew all this. Let me just show you a couple things here. Do you know what the Colosseum is in Rome? Have you seen it?
For lines and lines.
Yeah, okay, so it's like a giant stadium, right? They could not have built that without... Oh, that one's no longer available. They could not have built that without arches. Okay, well, I'll just have to watch this one. See if I can